Okay, this video is going to go over how to install and do a basic analysis with the tracker software, which is a particularly useful piece of software for analyzing video in physics. Okay, so I'll start from scratch here, go back to Google. And then once my computer wakes up, here we go. Then what we want to search for is tracker physics, and the first result that comes up should be it. We click on that, and if we scroll down here, there's lots of help on this window, but it's the best way to learn, I think, is to play around with it and then look for help when you need it. Okay, so the one to download is this Windows one. Now I've already downloaded it and run the installer and followed all the instructions. So I'm search on my computer for that and open that. There we go. And Tracker should open. And this program is completely free, which is cool, because it's so useful. Okay, now the first thing we need to do once we've opened Tracker is to find a video file that we want to analyze. And there we go. Here's a video that I shot. You'll notice that it's kind of pixelated. That's because I shot it at 480 frames per second so that I could get really clear, non-blurred motion. So there's a bit of a trade-off there. Okay, and then I'm just going to reduce the size of this thing and add a measuring bar. In fact, the first thing I'm going to do is add a set of axes to my video. And I'm going to put them in the video somewhere. And then I'm going to click on this little video clip icon. This allows you to define how time passes in the video. And by default it's defined to 30 frames per second. But in my video, I have 480 frames per second. So now the computer understands that every frame that clicks ahead, 1/480th of a second has passed. And because that means that I have a lot of files to analyze, I'm going to change the step size to 10 so that it only analyzes every 10th frame. Otherwise it gets ridiculous. Okay, and then I'm going to zoom in so I can see what I'm doing. At least to 200, maybe to 400. There we go. And I'm going to move this video to the frame where the ball first becomes visible, which is there. And by moving these little black arrows, it means that every time I play the video, it's going to start from there. And then I want to track the motion of this ball until it comes back down into this chimney that launched it, which is there. So I'm going to move the end. Oh, it's not letting me move it, but it's close enough to the end. Okay, I'll go back to the start here. Okay, then the next thing is we need to tell it how big the distances are. And I recorded this in front of a whiteboard on which I'd drawn a 10 centimeter line. And so I can tell the computer that this distance here is 0.1 meters. Okay. And then what I'm going to define this as the origin, the point where the ball leaves. And so because of I should have probably pushed the trolley the other way, but because of the way I pushed it, it's going to be moving in the negative x direction, and it's going to be moving up in the y direction. If things weren't aligned properly, I could also rotate these axes by clicking on the x-axis, on the little line that crosses the x-axis, but I think I did line it up pretty well. Now I don't know if that's straight. That's pretty good, I think. Okay, and then I need to create a point to track. So I'll create a point mass, which is now called mass A. And now I'm ready to track the motion of this point. And by holding down Shift, I change my cursor to a little crosshair. And then I find the point that I want to track, which is this ball, and I click on it, and it automatically skips ahead 10 frames because I set the step size to 10. And then I just click on the center of the point that I want to track, and I follow it until I've tracked the whole motion that I want to track. I zoomed in a little bit much there. The ball almost left the picture, but I think I got it. Okay, and then the ball comes back down. And the reason I've shot it with such a high frame rate is that if you shoot it at a low frame rate, what happens is that each frame is a blur, and it's hard to define exactly where the ball is. Now, I don't know if it's hit or not, so I'm not going to track that point because I think there might be another force acting on the ball at that point. So now I have a track of the motion. I can have a look at it. It looks like this. And so now all of this data in this table tells me time, x, and y. So the x1 is going into the negative. It's going at a constant rate into the negative because there's no horizontal force, which is one of the things that the students need to learn in projectile motion. And the other thing I want to show is this graph window, which is really quite powerful. I'm just going to make it as big as possible. So in this graph window, what we can see is an x-axis and a time axis. So if we click on this x, we can graph all kinds of other things depending on the experiment that we've done. We've done quite a simple experiment. What we're really interested in showing is that vertically, the motion is just accelerating at a constant rate. So let's have a look at the y motion. We can see that it makes this nice parabola against time because it's decelerating as the ball heads up. So as time progresses, it travels smaller and smaller distance with each passing frame, and then it accelerates on the way back down. So in fact there's a constant negative acceleration. And we can show this too if we change this to the y velocity, that in fact the velocity is decreasing at a constant rate. It starts at a positive 2.5 meters per second ish, and it decreases to 0 when it's at the top, and then it continues to decrease into the negative as it's heading back down, and it reaches a speed of, well, close to what it started at. I didn't quite track it all the way down. Okay, so that's kind of neat. And then the y acceleration looks kind of crazy at first because it zooms right in on the data that's interesting. You can see that this is only from 8 to negative 12. But if we zoom out a bit so that we include 0 here, and zoom out a little bit like that as well, it sort of looks respectable. The line is kind of centered around negative 10, which is what we would expect because the acceleration due to gravity is close to negative 10. The reason this line is much worse is because to work out the acceleration, it needs 3 points, really. And what you can do is you can also look at this graph and the corresponding points as they're being plotted. So if you play it, it kind of clicks along the points on the graph, and you can see where it is at each point. And it's possible to make really nicely scaffolded practical analysis tasks where the students really have to see the motion, which is a useful way to kind of combat the common misconceptions that students have about motion when they're coming into year 12.